All right, last class. We started in on light. Light being anything that's on the electromagnetic spectrum. We talked about how it's got two components. It's got the electric component, and then perpendicular 90 degrees to that, also in a wave thing, the magnetic part of that. And we talked about different parts of the electromagnetic spectrum. We did some calculations. We talked a little bit about color. So we had this nu equals c, which is the speed of light, nu's frequency equals the speed of light over the wavelength. We did a calculation with that. The only real trick here was that we needed to make sure we converted wavelength into meters so that our units actually work out to inverse seconds, and then we can turn inverse seconds into hertz. We talked briefly about the electromagnetic spectrum. We're not going to go super into depth into each of the individual categories, and talked about a couple of the trends, particularly as it pertains to the visible spectrum, and some like real basic details about some of the other categories. So you may know that light can be separated out by wavelength. White light contains a continuous spectrum, a rainbow of light. When it passes through a prism, it separates that light out, like in the famous Pink Floyd album. This also sometimes just happens randomly, like it's shining through the glass in your house and just like the right angle, or your like windshield. You can also use infrared light to do thermal imaging, and it's usually like heat mapped to visible light so that we can tell what's the hottest and what's the coolest. So usually it's like red areas are the warmest, and then blue or violet areas are the coolest. So this is how some like night vision tech works, is it just uses infrared light, since we can't see infrared light, blasts a bunch of infrared light out, it gets some infrared light back, or it just picks up what infrared light it gets back. Some of those high energy radiation forms, X-rays, gamma rays, stuff in that sort of area, we can also use, we being doctors, not me, can also be used to kill cancer cells. So they can direct beams of specific energies like through your body in a circular pattern, kind of all focusing it down on one particular area. And because all of those beams are basically shooting at the same area, all of that energy gets focused into wherever that tumor is. I think this is not especially common. I'm guessing that it's quite expensive. But it can be done. You can do it. And then the healthy tissue is still getting a little bit of radiation, but not quite as much. And there's some other interesting details about the way that that works. Another interesting thing that happens with waves is that you can get interference. This happens with like waves in a pool as well as with light and sound. So there's two types of interference. There's constructive interference, constructive interference. Construction is when you're building stuff. Constructive interference is when the waves are adding together. And we would call this in phase. So for example, we've got two waves over here that are in phase, meaning that they've got peaks in the same spots. They don't have to be perfectly overlapping, but you can kind of think of, we add up where it's above the node. The node is the point that's the zero in the middle. So anywhere where it's above, you add that to anywhere else on the other wave. If we had them slightly offset, then we would get like a wigglier shape. But basically the heights of these peaks add up, and so now the peak is twice as high. For sound, that makes it louder. For waves, that just makes the waves bigger. So if they're in phase, if they're lined up, matched up, synced up, then you can get larger waves out, louder sound, brighter colors, brighter light, that sort of thing. There's also destructive interference, like destruction, destroying things, the opposite of construction. So if the waves are out of phase, if they're opposites, we've got an example of out of phase down here. If they're opposites, then they interact so that they cancel each other out. And this isn't necessarily a complete cancellation, but it's going to result in some cancellation. So any waves that are up We've got a wave that's up here, we've got a wave that's down here. The up and the down cancel each other out, assuming that, you know, their frequency, there's like all sorts of details and stuff. And this is what like active noise canceling headphones do. They listen to what's around you, they pick up the frequencies, the noises, and then they send out an out of phase wave to provide destructive interference, and that's what cancels out the noise. That noise still exists, but because of the way that the waves work, it basically takes it out of your ears to varying degrees of success, depending on the device. So those can cancel each other out. Constructive interference, you may be familiar with like rogue waves out at sea. I think this is also the idea behind rogue waves. It's like suddenly there's an enormous wave, just a bunch of small waves all line up at one point randomly, and so then you get an enormous wave, which is kind of cool. Another property of waves is that they diffract. Diffraction, in my mind, is also sort of like what we were doing with the prism, where the light shines through and it separates out. So waves can also do that. So like sound waves, waves in a pool, light waves do it. When traveling waves encounter an obstacle or an opening in a barrier that's about the same size as the wavelength, they can bend around it. Traveling particles do not diffract. Particles travel in straight lines, so they're not going to diffract. Think of like if somebody throws a baseball through a tiny little hole, or somebody hits a really good three-pointer and it goes straight through the basketball hoop, it doesn't magically like diffract off to the side. It stays on its straight course. It stays on its straight path, unless it hits something else. Waves, on the other hand, if you send them through a small opening, will fan out in all directions. And if you do this with two slits that are separated by a distance comparable to the wavelength, so like on the same approximate size as the wavelength, not necessarily the exact same, then you can get an interference pattern because they're both diffracting next to each other, and then you've got all these different waves going on. And this interference pattern is characteristic of all light waves. So here's what diffraction looks like. So we've got our little barrier here, and we're looking at waves up on top. We're looking at particles down below. So for the particles, they're just traveling in the direction of these lines. So you can see where they hit the barrier, we're just saying that they fall dead or they bounce back. And the ones that make it through the slit, they just keep traveling in a straight line. However, for our waves, we're looking at wave crests. So these waves are coming out of and into the board. So we're looking at the peaks. And they hit this barrier and the slit. And the ones that make it through the slit, or the part that makes it through the split, then splits off and spreads out. So they're sort of like bending around the corner a little bit. Right, so these are all peaks or crests of the waves. We're not showing the troughs. So it's traveling sideways. And then it fans out. Fans out after the slit, which is kind of nifty. So that's one way that you can tell that something's got wave-like behavior, is if it diffracts. If it doesn't diffract, then it's got particle behavior. And here's a look at that interference from two slits. There's a link here. I think if I click that link, it breaks the stream, or it breaks the recording. So I'm not going to click it. But it's in the slides, so you can go and find the slides and click it on your own time. So we've got one light source, and it's sending out light, and we've got two slits. So the light is hitting these two slits at the same time because it's passing through the same light source. And then because the light has wave-like behavior, it hits those two slits, and it diffracts through that slit. So we've got the two different diffractions. And these waves that are coming out of the slits from the diffraction are going to hit at different points. So for some of these parts, they're going to hit, and one of them is going to be up and the other will be down, and so those will be destructive interference. Those are going to cancel out, and so you'll see a dark spot there. Others of these spots, they're both going to be up, and so you get a brighter spot there. And then in between, you get kind of a spectrum of a little bit of light, not a lot of light, lots of light. It's kind of fluctuating, little light, lot of light. So if we were to turn this screen or this film that we're looking at, we've got these really bright sections, and then it transitions to a dark section, and that's just because of the way that the distance that these waves had to travel there at different points in their cycle. So that's kind of cool. So that's, I think, most of what we're going to talk about with respect to wave behavior. We're going to switch gears and now talk about the particle behavior of light, because light also behaves like a particle. So historically, it's been observed that many metals will emit electrons when you shine a light on their surface. This is called the photoelectric effect. So the photoelectric effect says if you hit metal with light, it can emit electrons. This is related to, but slightly different from the way that solar panels work. That's the photovoltaic effect. But it's sort of a similar property, and we'll see some images so we can kind of wrap our minds around how the photoelectric effect works and is measured. So classic wave theory attributed this effect, this photoelectric effect, to the light energy being transferred to the electron. So the idea is the wave, the light hits the metal, and it transfers its energy to the electron, and then the electron gets ejected. Based on this theory, only the amplitude, the intensity of the light, will affect the emission of electrons. Any wavelength will work. It just has to be a strong enough amount of light to transfer that energy. So it predicts that if there's a dim light, then there would be some lag time before the electrons were emitted. So it would take some time. You'd have to hit it with light for a bit of time for the electrons to be emitted, because the electrons need time to absorb that energy. So you'd sort of be like charging up the electrons with low energy light, and then they finally get enough energy and they take off. So we've got a picture of a tube. There's no air in this tube, and we've got a metal surface that's hooked up to part of a current meter, and then the other part hooked up to the other part of a current meter, and we've got a voltage source so that electrons will fly off of this metal surface and be captured on the positive terminal, and that'll sort of complete the circuit. So we should see some movement in our current. So if light with enough energy hits this metal surface, we expect that it's going to dislodge some electrons. That energy gets absorbed by the electrons, they shoot off, and because they're negatively charged, they fly towards this positive terminal. They hit the positive terminal, and then that registers as a signal on our current meter. So some experimental observations. We talked about how we expect there to be a lag time with those low energy because we're kind of charging the energy up. So they did some experiments, and they found that a minimum frequency was needed before the electrons would be emitted, regardless of the intensity. So low energy light, if it's not the correct frequency, if it's got a low amplitude and it's not the correct frequency, it will not eject electrons. There's none of that charging up the energy and then it emits afterwards. There's no lag in that way. So the graph that we're looking at over here is the frequency of light increasing from left to right, and the rate of electron ejection. So a higher value on this chart means that we've got more electrons being emitted, and our zero is presumably here. So low frequency light, nothing's being emitted, and once we reach a certain intensity or a certain frequency, then we start to see suddenly a big jump, and now we've got electrons being emitted. For lower intensity light, we see less electrons ejected than for higher energy light, which makes sense. If you hit it with more energetic light, you would expect more things to come off. So high frequency light, anything that's past this threshold, from even a dim source, like this low intensity light, caused electron emission without any lag time. So there was no charging up, and there was this threshold frequency, which we didn't expect based on the previous predictions and hypotheses. So Einstein proposed an explanation for this. He proposed that the light energy was delivered to the atoms in packets, little bursts of energy. We call a packet of light a photon or a quantum. We've probably heard photon more frequently. So these are the little smallest piece of light. If you can try to imagine light being made up of little pieces, a photon or a quantum is the smallest little piece of light. And the energy, the amount of energy contained in one of these little packets of light, you could think of them maybe as little balls of light, even though that's probably not correct. So in one of these little balls of light, the energy that they contain is directly proportional to its frequency. So if you've got higher frequency, you're also going to have higher energy. It's also inversely proportional to its wavelength. So if you've got a really long wave, rebooting. If you've got a really long wavelength, you're going to have really low energy. If you've got really short wavelength, you're going to have high energy. And there's a proportionality constant called the Planck's constant. Planck's constant gets the symbol H. And so we've got a couple of formulas. We've got energy equals Planck's constant times nu, frequency. We've also got energy equals Planck's constant times c, the speed of light, divided by lambda, which is the wavelength. Those are two equations and the Planck's constant that I typically give on exams. So you don't have to memorize them, but you should know how to use them. To practice using them, we've got this problem. A 100-watt light bulb radiates energy at a rate of 100 joules per second. The watt is a unit of power, and it's defined as 1 joule per second. If all of the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? So we're looking for photons per second, and we'll just give 3 significant figures for our value. So these E values that we see up here is energy per photon. If I'm remembering correctly. Okay, where to start? Well, we've got some things that are given to us. We've got energy for our light. We're also given a wavelength. Since we have wavelength, we want to pick the version, we want to pick the equation that has wavelength in it. So we're going to use the one on the right, hc over lambda. So we're going to use E equals h, Planck's constant, c, speed of light, over lambda, since we have lambda. And I'm going to copy down the Planck's constant so that we can scroll down. Sorry, joules seconds, not per second. Okay. So we've got hc over lambda. H is a constant, that's Planck's constant here. C is also a constant. C is the speed of light. 3.00 times 10 to the 8 meters per second, so meters over seconds. So our energy, again, this is for one photon, one packet of light, is 6.626 times 10 to the minus 34 joules seconds times C, which has units of meters per second. So on the top, the seconds will cancel out. And then underneath that, we've got our lambda, which is 525 nanometers. If we put in nanometers, do our units cancel out nicely? They do not. So we would have meters on top, we have nanometers on the bottom. So what we're going to do is we're going to sub in, for nano, we can sub in 10 to the minus 9, because that's what nano means. It's one of our small units. In intervals of 3, we've got milli is 10 to the minus 3, micro is 10 to the minus 6, nano is 10 to the minus 9. And then we can see that our meters will now cancel. We'll be left with units of joules. So we'll grab our calculators. We'll put in 6.626 e negative 34 times 3e8 divided by 525 e negative 9. This is 3.786 and some other numbers times 10 to the minus 19 joules. How many photons have this amount of energy? How many photons does it take to make that amount of energy with this wavelength? 1. This is the energy for one photon. And so we can write under this per photon. Because this would give us a lot of the points if this was a short answer question. But we asked how many photons are emitted per second. So we need to use this 100 joules per second now. So we've got 100 joules per second. And this number that we found, this really small number, is the joules per photon. This gives us a conversion between joules and photons. So we are going to take our 100 joules per second and divide by this joules per photon. And look at what the units do when we do that. So we'll have 3.786 some other numbers times 10 to the minus 19 joules. The photons part flips to the top. Joules cancel. And the units that we're left with are photons per second, which is what we are looking for. And we're going to get a crazy number. So this light is 2.64 times 10 to the 20 photons per second. That's a lot of photons. Questions about any of those bits? So I think the tricky part of this one is just remembering that the energy here is for one photon. One little packet of light has that much energy. So we can say that it's per photon. That lets us make it a conversion factor. So this amount of energy equals the energy for one photon. All right, testing what we remember from last class. Arrange these three colors of visible light, green, red, and blue, in order of increasing wavelength, frequency, and energy per photon. And I'll give you a little bit of time to do this. Okay, that was a little bit of time. In the rainbow, what's our outsidemost color? What's the top outside arc of the rainbow? It is red. Red's one of our colors here. Which would come next, green or blue? If we're working our way in. Green, right? And then on the inside, just for these colors, we would have our blue. Which of these is going to be the longest? If we straightened out the curves of the rainbow, which one's going to be the longest line? The red. Red is longest, which means that green is in the middle and blue is shortest. This corresponds to the order of their wavelength as well. So blue, since we're going order of increasing, blue is our shortest. Then in the middle we've got green. And then the longest is red. What's the type of light that gives you sunburn? UV, what does UV stand for? Ultraviolet. Which of these colors is closest to violet? Blue is closest to violet. Ultraviolet gives you sunburn. That's a lot of energy. Blue is closest to that. Blue's our highest energy. Green would be lower, and red would be lowest. So our order is flipped. So red's our lowest energy per photon. In the middle is green. And the highest energy, because it's closest to violet, is blue. And the one that we don't really have a trick for is frequency. Frequency and wavelength are inversely related. So remember we talked about long waves are going to have low frequency. So high length, low frequency. Because they're so long, it takes them more time to pass through a point. If you've got really short waves right next to each other, more of those are going to pass through a point. So the frequency is the same as our energy per photon. It's the opposite of our wavelength. So it's the same as our energy, opposite of wavelength. Questions about those? This is the equation that shows us that they're inversely related. So if we make wavelength bigger, frequency gets shorter. If we make wavelength smaller, frequency gets bigger. Higher frequency, more frequency. All right, if I give you a question and I ask you for which color in the visible light spectrum is the most, and I give you just most of anything, and I give you the options of green, red, and blue, there's one of these that you should never pick. What's the color that you should never pick? If I ask you for something that's the most, the highest energy or the highest wavelength, it's green. because green is always in the middle. So if you're given a question like this, where it's asking for what's the highest energy, what's the highest frequency, what's the highest wavelength, even if you don't remember the order, pick one of the outermost ones. You narrow yourself down to a 50-50. So green is never the most. The order is always going to be rainbow order. It's either going to be from red to violet, or it's going to be backwards. It's going to be from violet to red. It's always going to be in color order. So those are my tips and tricks for you. Okay, going back to our photoelectric effect and the ejected electrons. So we've got energy with a sufficient frequency hitting the metal, and it's ejecting electrons. If we have a photon at the threshold frequency, that's where our graph shot up. That's the minimum frequency that we need to eject an electron. If it's at the threshold frequency, it has just enough energy to dislodge a single electron from the metal. And we give this Greek letter phi, we call this the binding energy of the electron. So that's basically how strong is or how well is the electron held. So a really high value means that electron is not going anywhere. Really low value means it's really easy to dislodge the electron. So how strongly the electron is held in the metal. If you hit the metal, if you irradiate it with a higher frequency photon, higher frequency means more energy, the electron absorbs more energy than is necessary to escape. So that electron is still getting all of that energy, but now it's not just leaving, it's also taking that extra energy with it in its little rucksack. So that excess energy becomes the kinetic energy of the ejected electron. So excess energy is absorbed and becomes kinetic motion energy. You can sort of think of it as like it's being like all the electrons are kind of held in place. They've got like little strings or something on them. When they get hit by the photon, some of that energy goes to breaking the little ropes or whatever is holding them in place. So that's going to take some of the energy. And then they're going to have any excess energy become kinetic energy. So we lose a little bit because of the binding energy, this phi symbol. And then the rest turns into kinetic energy. And so kinetic energy of our ejected electron the kinetic energy of the ejected electron is the energy of the photon, and the energy of the photon is h Planck's constant times nu, which is frequency. That's one of the two forms of the energy equation that we saw before. This is the one we didn't use, minus the binding energy, how tightly the electron is held in the metal, which has the symbol phi. Okay. So testing our conceptual understanding, let's say that a metal will eject electrons when it's struck by yellow light. I don't have a color for yellow light currently. So it's hit by yellow light. That's awful. Yellow light, what's going to happen if the surface is struck with ultraviolet light? So think about, how does yellow light compare to ultraviolet light? If yellow light ejects electrons, what will ultraviolet light do? Is it that no electrons would be ejected? Or is it any of these circumstances where electrons will be ejected? They'll have the same energy, they'll have greater kinetic energy, they'll have lower kinetic energy. How does ultraviolet light compare in terms of its energy to yellow light? It is C. Why is it C? UV light has more energy. Than yellow light. Yellow light does not give you sunburn. UV light does give you sunburn. It's got more energy. So UV light has more energy, and excess energy turns into kinetic energy. For the ejected electron. So if yellow light was our base, that's the minimum amount of energy we needed to eject electrons. If we ramp the energy up, it's still going to eject the electrons. They're just going to have extra energy when they're blasting off the surface of the metal. If we hit it with red light, which has less energy, presumably no electrons would be ejected. If they were, they would have less kinetic energy compared to yellow light because red has less energy than yellow. Questions about ejection? Okay. So light is weird because it exhibits what we call wave-particle duality. So it behaves like a wave sometimes. It also behaves like a particle sometimes. And the way that it behaves depends kind of on the test that you're doing with it, which is fun. We might have some examples of that. But we'll jump into atomic spectroscopy. This leads into more of the concepts stuff, the weird, hard to understand, not intuitive stuff that I was alluding to before last lecture. So when atoms or molecules absorb energy, that energy is often released as light energy. So one of the ways that atoms can get rid of excess energy is by emitting a photon of light. They don't really have a lot of other options, like they could run into something and impart like physical kinetic energy into stuff. Oftentimes though, they're exhibiting or emitting that as light energy. So for example, fireworks are different colors because of the different materials that are used. They give them a bunch of energy, usually by burning them, and then it causes them to emit light. Neon lights, it's a similar thing, but you're not burning the neon gas. You're just charging it with a bunch of electricity to give it energy to make it glow a certain color. So over here on the right, we've got a bunch of different lamps. So we've got hydrogen, helium, and mercury lamps. I'm not 100% sure off the top of my head which is which, but these are all different elemental lamps. So different elements also produce different colors of light, sometimes depending on the amount of energy that you put into them. And then we've got, of course, a neon sign. This one's red, and we've got a bunch of fireworks with different metals and things in them. So atomic spectroscopy is useful. The color of light that you get emitted can be a blend of a bunch of different lights. And so in order to figure out which colors of light are being emitted, we have to pass it through a prism. Like we saw with white light, you send the white light through a prism and it fans out into a rainbow of colors, like a nice continuous rainbow of colors. If you do this with an atom or a molecule that you've caused to light up, then the pattern that you get out is called an emission spectrum. We'll see a bunch of pictures of emission spectra. This is like a rainbow, sort of. It's not really a rainbow, so I'm going to put that in quotation marks. rainbow of colors emitted. The spectrum part is referring to the rainbow, so it's like a range of colors. Unlike white light, the rainbows that we see in the sky, the ones that come through our windows, if you shoot white light through a prism, these ones are not continuous. So they're going to have gaps in the colors. So we're going to have some bright lines, and those bright lines will be at specific wavelengths, and then in between those lines, we're going to have complete darkness. There's no light being emitted in those ranges. And an emission spectrum can be used to identify an element. It's sort of like a fingerprint or a barcode, but for a specific molecule or element. And these are interesting because they can't be explained by classical physics. So we need new physics to be able to do these. So this is what a setup might look like in a bunch of emission spectra, including a white light spectrum for comparison. So if we're doing atomic spectroscopy, we take our sample, we put it into a lamp, we hit it with a bunch of energy, kind of like a neon sign lamp. Hit it with a bunch of energy, you pass that light through a slit. This gets it into a nice narrow column of light. Then you pass that slit of light through a prism, and that's going to separate all your colors out, just like you would with white light turning into a rainbow. And you separate that out onto film or like a digital surface or something, and then you can see which colors of light were absorbed, or were emitted, sorry. So we hit the photographic film, you develop the film, and for hydrogen, we've got this reddish light, we've got a bluish light, and then there's like a couple of violet lights. That's all we see in the visible spectrum. For helium, we've got a couple more lines. If we move up to something bigger, barium's got a bunch of lines. Oxygen, we've got a lot of lines. There's a little bit of like blending as well, but these bright lines are what we really care about. So we're not too concerned about like if there's a little bit of color in between them. It's really just those sharp lines that are the things that we care about. And the neon one down at the bottom is a little bit fuzzy, but you can see that there's a lot of different lines in there. Another thing that I want to point out while we're here is if we look at the helium spectrum and the barium spectrum, we didn't just add colors of light to our helium spectrum. So like for helium, if we look at the like blue region, we've got 3 bars that are kind of in this blue region, and they don't line up with the ones that are in the barium spectrum, which only has 2. Similarly, our yellow in the helium spectrum almost lines up with the barium spectrum one, but not quite. And this is a common pattern that you'd see if you looked at a lot of emission spectrum. So we could identify some of these elements based on where those wavelengths are, as well as like how many lines there are. That could give us an idea of the size. I think you can also do absorption spectra. I don't think we really talk about that much in here though. So I think what we're looking at here, on the top we've got an emission spectrum, and then on the bottom we've got an absorption spectra. So if you like took mercury and you hit it with white light, the dark patches correspond to the light patches where it emitted light. It can also absorb light in those regions. So that's why we're seeing these dark spots. I wouldn't worry too much about it other than just like we mentioned it. So like if somebody asks you about it in the future, maybe your brain will be like, oh yeah, I think we talked about that briefly. Another thing that you can do, this is sort of similar to the emission spectra, is you can identify elements with flame tests. These are a little bit of like hit or miss. Sometimes you have to have like the right concentration. There's some details parts of it. But if you burn these different elements, right, you can see we get different colors of flames. So sodium gives us this really nice orangey light. They used to actually use this color of light for like street lamps, which was really problematic. Potassium gives us like this purplish color. Lithium's a nice red. Barium's sort of like a white yellow kind of color. And there's a bunch of different elements and compounds and stuff that you can burn that produce different colors, and that's how they make all the fun colors in fireworks displays. It's basically flame tests, but up in the sky. Okay, so people in the past have looked at these emission spectra and thought, wow, that's really weird. That's interesting, the way that they're spread out, where those lines show up, what wavelengths those correspond to. And Johannes Rydberg analyzed a lot of those atomic spectra and found out that they could be described with an equation that involves the inverse square of integers. Which sounds scary. It's not quite as scary as it sounds, I think. But this equation gives us a little insight into why those atomic spectra are discrete. So discrete just meaning that we've got individual lines rather than continuous. They're showing up at specific points. It also gives us some insight into why atoms are stable and also why his equation works. And his equation is this one. We could also write it like this. It's the same thing, it's just maybe a little easier to visualize. So our lambda over here is still wavelength. R is the Rydberg constant. M and N are some integer values. I think technically we could also call those counting numbers, but I'm not a math major, so I could be wrong there. But like 1, 2, 3, 4, 5, only, I guess it would work for negative numbers because they're squared, but that's the idea. We're not doing like 1.5, 2.5. So the inverse means we're dividing the numbers on the bottom, the square, they're squared, and they're integer, they're 1, 2, 3, 4, 5, etc. We'll use Rydberg's equation a little bit, but kind of just plugging numbers in to show that stuff works. Might show up on the exam once. Okay, so getting into the atom. We have to talk a little bit about what the shape of the atom is like to be able to show you why Rydberg's equation and some of the other stuff is interesting, relevant, etc. So our atom contains a tiny, dense center called a nucleus. The nucleus contains basically the entire mass of the atom. The vast majority of the mass of the atom is in the nucleus because the nucleus has our protons and our neutrons. It's also positively charged because of the protons, and the amount of positive charge in our atom balances the negative charge of the electron. Atoms are generally neutral unless they're ions. So the number of protons that we have in the nucleus, like for argon we've got 18, is going to balance the number of electrons. So we know that argon also has 18 electrons. So we've got our little dense center, all our mass, all our positive charge, and then around that there's a bunch of empty space, and that's where our electrons are moving around. And they have basically no mass compared to our nucleus. So this was Rutherford's model. There's some issues with Rutherford's model. So one of those issues is that he had electrons moving around. You could think of them like orbiting in whatever pattern or just flying around. Electrons are charged particles, and they're moving under Rutherford's model. That's problematic because moving charged particles give off energy. So if our charged particles are moving around, we would expect them to constantly be giving off energy, which might cause them to glow. Not necessarily in the visible spectrum, but in some spectrum. And since they're giving off energy, they should also lose energy, crash into the nucleus, the atom should collapse. But it doesn't because we're here. And so this model of the atom doesn't explain some things. right? There's some issues. So Bohr developed a model. Niels Bohr developed a model. This is slightly different from Rutherford's model. So in Bohr's model, electrons travel around the nucleus in circular orbits. This is sort of like planets around the sun. So this is something that we can we probably have a little bit of a framework because we've seen models of the solar system where the planets are circling around the sun. That's what our electrons are doing, and the sun is our nucleus. And just like the planets existing on kind of basically their fixed track, the orbits where the electrons fly on exist at specific fixed distances. So the orbits are little electron flight paths, exist at fixed distances from the nucleus. And the energy of each orbit is also fixed. We can also call that quantized. So it's got a specific quantity value associated with it. The amount of energy is related to the electron's position. Close orbits are lower energy than further orbits. So the electrons that are closer or on the closer tracks are going to have lower energy. The electrons that are on the further tracks are going to have higher energy. And again, these are fixed values. So our electrons in our atom can only be on these fixed orbit tracks, and so they have to have specific amounts of energy associated with those tracks. And here's a little bit of a model of that. Here's showing some of this. So we've got our nucleus here, and then we've got our orbits. We're just showing half of them. Our orbits, and we number them starting from 1 as our lowest number. This is our innermost track or orbit. And then outside of that, we've got our n equals 2, 3, 4, and 5. And you could keep going and making up new orbits if we needed to. So these ones on the inside are the lowest energy. And these are at fixed distances, so we can't have an electron, for example, between our 2 and 3. It has to be on the 1, the 2, the 3, etc. It has to be on one of these tracks. And the electrons can emit radiation when they jump from a higher energy orbit to a lower energy orbit. To go from a higher energy orbit to a lower energy orbit, they're going from high energy to low energy. To do that, they need to lose energy. And the way that electrons can lose energy is by emitting a photon. So they can emit some light as they do that to lose energy. So electron can emit a packet of light, a photon, to lose energy. Similarly, if we've got an electron that's like on this n equals 2 and it gets hit with some light, it could jump up to the n equals 4. So it can absorb energy to jump up to a higher orbit as well. And since the distance between these tracks is fixed, the amount of light that an electron emits when it jumps from 4 down to 2 is always going to be the same energy. So fixed distances between orbits means energy, in this case we're looking at it as color, of light emitted is also fixed. Or set, I guess might be another way to say it instead of fixed. So this is really cool for a couple of reasons that I guess we'll get to. All right, so some more things about our Bohr model Again, this is our Bohr model. So our Bohr model, our electron is never going to be observed between states, between orbits. It's always going to be on one of these tracks. The energy of the photon emitted is the energy difference between the two orbits. And we can calculate the energy of those orbits based on the wavelengths of our lines. This is not our most up-to-date model, but it's still worth talking about because it brings some important information to the table. And it's still going to be useful in many cases to think about the Bohr model to help us wrap our brains around the models that we're getting to. So we're still going to be, I'll still be referring back to these orbits, these n equals 1, n equals 2, n equals 3 levels, as we're moving onto our more advanced quantum mechanical model. So it was ultimately replaced by our more complete quantum mechanical model, and the quantum here just meaning we're talking about the smallest quantities, mechanical meaning how does it work. So we're interested in how do the smallest possible things work. We're thinking about electrons and atoms and really, really small stuff. How do they work? Because they don't behave the same as we do. For more on how those things don't behave the way that we do, we've got Louis de Broglie to thank. So he proposed in 1924 that particles could have wave-like character in addition to their particle character. So this is not like with light where we've got wave-particle duality. This is saying that things that behave as particles, like baseballs or flying atoms, also have wave-like character. The wave nature of the electron is most clearly seen in electron diffraction. So we send it through the little slit and it diffracts out even though it also is a particle or behaves like a particle. This part is like unbelievably confusing. So the interference pattern of an electron is not caused by pairs of electrons diffracting through a slit. It's caused by an electron interfering with itself. I think Veritasium has a video about this. There's like a big science creator on YouTube, I think, that has an explanation of this property, but I don't know what it is off the top of my head. See YouTube for more on this. Not my channel. Again, I think it's Veritasium has a video about this, but it could be somebody else. It's really weird. Okay, so proof that electrons have wave nature came 3 years after de Broglie's proposition with a demonstration that a beam of electrons produces an interference pattern the same as waves do. So you've got an electron source over here, a beam of electrons. They can go through two closely spaced slits, and you get an interference pattern the same as waves exhibit. But electrons, we normally we think of them as particles. So this is weird. This is exciting. If electrons behaved only like particles, then we would expect two bright spots. We would expect them to go through the slits, keep traveling in a straight line, and then we would just get them hitting kind of on the path when they go through that. But that's not what is seen. They diffract as well, which is wave behavior. So we've got particles that are exhibiting wave behavior, and this is very weird. The wave nature of the electron is an inherent property of individual electrons. So the electrons do exhibit some wave behavior. And de Broglie, that person we were talking about before, predicted that the wavelength of a particle is inversely proportional to its velocity, and so we get this de Broglie relation. So we've got our wavelength, our de Broglie wavelength. is equal to our Planck's constant, same Planck's constant that we saw before, over the mass of the particle times, I think this one is velocity. It's a little bit harder to tell in the script the way that it's written. Pretty sure it's velocity. Okay, so using our de Broglie relation, copy it down here for us. And copy down our Planck's constant. What is the velocity? So we're finding velocity of an electron that has a de Broglie wavelength. So that's our lambda here. Approximately the length of a chemical bond. Assume the length, our de Broglie wavelength, to be 1.2 times 10 to the minus 10. Meters. So we're finding V. We're given lambda, our de Broglie wavelength. H is a constant. M is mass. So we're going to need the mass of an electron in I think we might need it in kilograms. I don't know what it is off the top of my head, so we're looking it up. Electron mass. .10 and a bunch of other stuff. We probably don't need all of these decimal places. And this is in kilograms. Okay, so we can get to work. We are trying to find V, velocity. So we're going to rearrange. So we're going to swap the places of the lambda and the V. If something's on the top on one side, you can make it on the bottom on the other side. If something's on the bottom on one side, you can put it on the top on the other side. That's the algebra shortcut. So this turns into V equals H over M lambda after we do the little bit of algebra. And we can start plugging stuff in because we've got everything we need. So our H value goes on top. Joules times seconds over our M value. I'm going to dot this to save some space with units of kilograms. And we also have our lambda, our de Broglie wavelength, 1.2 times 10 to the minus 10 meters. What units might we expect to get for velocity? Meters per second. We expect probably meters per second, because those are our SI base units, meters and seconds. Which of our units cancel out here? It looks like none of them cancel out. However, you might recall that joules has a different way that we can write it. if I'm remembering correctly, joules is kilograms meters squared per second squared. And I'm pretty sure I'm remembering correctly. So we're going to sub in kilograms meters squared per second squared. This cracks our units wide open. You could put the numbers in and you'd get the right answer. You just wouldn't know where the numbers came from or the units came from. So this kilograms in joules is why I was saying I'm pretty sure we need mass in kilograms. That's so that they cancel out. If we use the mass in grams for some reason, the units wouldn't cancel out. Okay, so now that we've done that, we've got kilograms on the bottom, kilograms on the top, so those cancel. We've got a seconds up here. We've got the inverse seconds squared. So one of those seconds cancels. We've got the meters on the bottom. We've got the meters squared on the top. So those also cancel, and the units that we're left with are, in fact, meters per second. So we do a weird unit substitution. It's not really weird, it's just unusual for us. We're not used to it yet. We do that little unit substitution and everything works out okay. Questions about that? Okay. Plug all this into our calculator, and we get out 6.1 after rounding times 10 to the 1, 2, 3, 4, 5, 6 meters per second. The full number that I got out of my calculator was this. We rounded 2 sig figs because of the length that we were provided. All right, another thing that we can do with the de Broglie wavelength, you can also calculate de Broglie wavelength for like macroscopic things that are in our realm of the world, our size of the world. You can calculate it for macroscopic objects. So quantum mechanical theory is universal. It applies to everything. So like a thrown baseball should also exhibit wave properties. Why don't we see baseballs exhibiting wave-like properties if we go to a baseball game? Where like a quarterback throws a football and it like passes in a small slit between two people. Why don't we see it diffracting and exhibiting this de Broglie relation property? Is it because the baseball's mass is large and so its de Broglie wavelength is minuscule and insignificant compared to the baseball's size? Is it because baseballs don't have charge and so quantum mechanics doesn't apply to them? Or is it because that baseballs are just immune to quantum mechanics? Any ideas about which one it's not? Yeah, it's not C. We're told that quantum mechanical theory is universal, so it should apply to baseballs. You can actually do this calculation if you wanted to. You could calculate the de Broglie wavelength of the baseball. I think there's some fun examples of that. Maybe not in our slides. Lambda equals h over mv. So let's say that the mass is 0.142 kilograms. The answer is A, by the way. It's A, but just to show you, I thought it would be fun to actually do the calculation. Times 10 to the minus 34 joules seconds. And let's say that we are Randy Johnson. and we can hurl a baseball at 100 miles per hour. So our velocity is 44.704 meters per second. The de Broglie wavelength of this baseball being hurled at the unbelievable and scary speed of 100 miles per hour is going to be magic. We get meters out. Okay, the de Broglie wavelength of the baseball, 1.04 times 10 to the negative 34. So this is like nano is 10 to the minus 9. So this is like nanometers. This is like smaller than electrons, I think. So it's completely inconsequential with respect to the size and the mass of the baseball. So that's why we don't see baseballs diffracting, even if they're pitched at 100 miles per hour. Any questions about any of our new stuff today? Great, then we'll wrap up there.